Hello class, let's discuss open channels. Open channels are conduits in which fluid flows with a free surface. Examples of which are rivers, drainage ditches, sewers, canals, and any structure that conveys water with an open free surface. In an open channel flow, the hydraulic grade line coincident with a stream surface and the flow may be uniform or non-uniform. In an open channel, these are the most common shapes that are being used. In an open channel, we have a rectangular, parabolic, triangular, trapezoidal, and circular. In order for us to obtain the velocity in the open channel, we can compute that using the Chezy formula or the Manning. For the Chezy formula, here's the equivalent solution for the velocity. It is equals to C, or the Chezy coefficient, multiplied by the square root of Rs. R is the hydraulic radius and S is the slope of the energy grade line. Hydraulic radius can be computed by dividing the cross-sectional area of flow by the wetted perimeter. So the cross-sectional area is this one, while the wetted perimeter is the perimeter which is in contact with the fluid. Okay, so say if this is your open channel, this is your wetted perimeter only, excluding the open free surface. While the slope of the energy grade line, if it is a uniform flow, means that the slope or the bed slope along this open channel will be your equivalent slope. Okay, but if it is not uniform, we will refer to the energy grade line for the equivalent slope. So going back here, so if this is your energy line, if it is a non-uniform flow, your S that should be used in the formula is this energy grade line. But if it is uniform, just use the slope of the bottom of the channel. Okay. Next, in order for us to obtain the value of C, we can use the Manning, which is equals to 1 over n, R is to 1 over 6, or the cutter. Both units here are in SI. Okay, either Manning or cutter. In order for us to obtain the Chezy coefficient, n is the roughness coefficient. But the most commonly used formula in solving these problems in open channels is the Manning's formula. Manning's formula is equivalent to the velocity is equals to 1 over m, the hydraulic radius raised to 2/3 multiplied by s raised to 1/2. That's in meter per second. And if we're going to determine the flow rate in the channel using Manning's formula, since the flow rate is just equals to the area times velocity, we just multiply area in order for us to obtain the flow rate. Okay, this is now your equivalent solution. This is in SI units. But if we are required to determine the velocity as well as the flow rate in English system, this is your solution. Just multiply the conversion factor of 1.486. Okay? Now, come now to the most efficient sections. Most efficient sections are also called as the most economical section of the open channel. The most efficient section gives us the maximum discharge within the open channel. So that's why it is essential for us to determine the most efficient section for us to have a design of a channel that is very efficient in terms of discharge. Okay, for rectangular sections, the the most efficient section should have a dimension of width b, which is equivalent to twice its depth. Okay, or b equals to 2d. Okay? This length b here should be twice the value of its depth. Also, if we are going to determine its hydraulic radius, that will be equivalent to d over 2. Again, hydraulic radius is the area, sectional area, divided by the wetted perimeter. Okay, so that will be d over 2. For trapezoidal sections, for the most efficient section, the top width is equals to the sum sides. It means that this distance x here, the top width, should be equivalent to the sum of the sides. Y is a 1 and y is a 2. Also, the hydraulic radius should be equals to d over 2. Okay, so that's the requirement for us to obtain the most efficient section. Take note that the most efficient section of a trapezoidal open channel is the half regular hexagon. So if you have a hexagon, okay, just take the half of it, and this open channel is the most efficient section for a trapezoid open channel. That means that we have an interior angle that is equivalent to 120 degrees, or an angle here of 60 degrees, 120, 120, this is 60. Okay, so depending on the type of problem that we will encounter on trapezoidal section, that's why we have these conditions to be met in order for us to have the most efficient section for a trapezoidal open channel. So it is also essential that we should consider this. Top width is equals to sum of sides, and the hydraulic radius should be equals to d over 2. Next, for triangular section, the most efficient triangular section is a 90 degrees V notch. Okay, an angle of 90 degrees. That's the most efficient section for triangular. Okay, for circular section, if we have a total depth d, or the diameter of the open channel, for us to have a maximum discharge, it should have a depth of equivalent to 0.938 multiplied by the diameter d. So that's for circular section. Now, for specific energy, it is the energy per unit weight relative to the bottom of the channel. So what would be that? Equivalent specific energy of any section of an open channel. We use this solution. It's just the sum of v squared over 2g, or that's the velocity head, added by the depth of the fluid. Okay. Next, for the Froude number, it is the ratio of initial force to gravity force. In order for us to obtain the Froude number, F is equals to V over the square root of GL. For rectangular section, that L is your depth of flow, which is this D. Therefore, the Froude number is equals to V over the square root of GD. For the critical depth, the critical flow, it is the variations of specific energy with depth at a constant discharge shows a minimum in the specific energy at a depth called the critical depth, at which the Freud number has a value 1. So if we have obtained a Freud number equivalent to 1, it means that we are at a critical depth. A critical depth is also the depth of maximum discharge when the specific energy is held constant. So how can we determine this critical depth? Critical depth for rectangular channel is equals to the cube root of q squared over g. So take note that this q here, this q is the unit discharge. Okay, it's the unit discharge, which is equivalent to cubic meter per second per meter width. So it means that if we have a discharge q in this open channel, in order for us to determine this lowercase q, we just have to divide the discharge by the width of the channel, which is b. So that's your lowercase q in this solution for rectangular channel. But if we have a section that is irregular, it is of different shape other than rectangular channel, so we can use this solution right here. The ratio of q squared, which is the discharge in the channel, divided by g, is equivalent to a cube, or the cross-sectional area of the channel, divided by the top width b. Okay, just use this equation and we'll be able to determine this critical depth d, which can be obtained here in this area. This dimension d can be obtained in determining the cross-sectional area of the open channel. Okay, that's how we obtain the critical depth. Okay, so let's now solve some problems. Okay, sample number 1. This is CE board May 2010. A rectangular channel 5.5 meters wide and 1.3 meters deep is lined with a smooth stone, well laid, and has hydraulic slope given, which is 0.002. N is the roughness coefficient, that's 0.013. Question in letter A: what is the capacity of the channel in cubic meters per second? So here, using Manning's formula, Q is equals to area over N multiplied by the hydraulic radius raised to 2/3 S raised to 1/2. So let's solve first the area, which is equals to 5.5 multiplied by 1.3 meters. That is equals to 5.5 times 1.3, 7.15 square meter. After that, we can now compute the hydraulic radius, which is equals to the cross-sectional area divided by the wetted perimeter. So solving the hydraulic radius, we already have the area, 7.15 square meter, to be divided by the wetted perimeter. So let's just add 1.3 times 2, then add the bottom lining 5.5. So 2 times 1.3 plus 5.5. That's your hydraulic radius. So we have 7.15 divided by 2 times 1.3 plus 5.5. So the hydraulic radius is 0.8827. Okay, the unit is in meters. We can now solve the flow rate. We have an area of 7.15 to be divided by 0.013, the N, hydraulic radius 0.8827 raised to 2/3 times the slope, which is 0.002 raised to 1/2. So the Q is 7.15 divided by 0.013 multiplied by 0.8827 raised to 2/3 times 0.002 raised to 1/2. Okay, flow rate is 22.6335 or 36 if we have 4 decimal places. Okay, that's in cubic meters per second. That's the answer for letter A. For letter B, question is, what savings in earth excavation could have been offered by using the more favorable proportion, or what is being referred to here is the most economical section or the most efficient section, but still adhering the same delivery or the discharge and its slope. So in this given dimensions kasi, this is not the most economical section, but uh, if we use the most economical section, the question here is what savings in earth excavation could have been offered if we use the most economical section. So let's find first the dimension of the open channel, rectangular channel that is in economical section. Okay, most economical. So according to our lecture, the most economical section should be the depth should be the width should be twice its depth. So this is 2D. So it says there that if we use the same flow rate Q using the same formula, R raised to 2/3 S raised to 1/2, using the same Q and slope, uh, what will be the savings in excavation? So let's determine first what is the dimensions of this economical section. So let's determine B and D. So let's express both dimensions in terms of D, since the width B is twice its depth. So let's just represent this width B into 2D. So substitute now 22.6336 cubic meters per second equals to area. Okay, so the area here is D times 2D. So that's 2D squared over N. N is 0.013. Hydraulic radius. Based on our lecture, the hydraulic radius of the most efficient section of a rectangular open channel should be D over 2. So that will be raised to 2/3. Then use the same slope of 0.002 raised to 1/2. So the unknown here is D. So I will directly solve D in this equation. That's 22.6336 equals to 2D squared over 0.013 multiplied by D over 2. D over 2 raised to 2/3. Then multiply 0.002 raised to 1/2. Okay, let's solve for x, or the unknown variable d. So the d is 1.8586 meters. That's the depth. So therefore, multiplying it by 2, we can determine the width b, which is 2d. So 2 times 1.8586. So the width is 3.7172 meters. So using these dimensions, b and d, okay, we will now subtract the area of the given dimension by the area of the economical section. It means that the difference in their area, that will be the savings in earth excavation per unit length. Okay, so that's your savings in excavation. So the area from the given dimensions earlier is 1.3 by 1.5. So this is 1.3 meters times 5.5 meters subtracted by 1.8586 and 3.7172 meters. Okay, so let's solve this. The answer is 1.3, 5.5, 1.8586, 3.7172. Okay, the answer is 0.2412. 0.2412 square meters. Okay, that's the saving in excavation per unit length. Okay, because depending on the length of this open channel, that will depend on the savings in volume of excavation. Okay, since the length of this open channel is not given, so we can just only express it by the area per unit length. Okay, for question number 3, or letter C, what savings in lining per meter length by using more favorable proportion, or the most economical section, but adhering the same delivery and slope? So what will be the savings in lining? Okay. So means here that what will be the savings, since we will put a lining of smooth stone. So again, comparing the two dimensions, if we use this, what will be the total perimeter of this lining right here that you will be putting on the open channel, that will be saved when you use the most economical section. Okay, this lining that we will be putting here. Again, our unit here is in meters, but it should have been a unit of area, because we should uh, we should have a length of this, a value for the length of this open channel. But since it is not given here, so again, it will be assumed that the lining is in meter per unit length. Okay, an imaginary length of 1 meter. So again, what will be the savings in the lining? So let's just compare again. Subtract the uh, wetted perimeter, okay, wetted perimeter of the given, and the wetted perimeter of the most economical section. That will be your savings in lining. So let's directly solve this. We have 1.3, 1.3, and 5.5. So that's 2 times 1.3 times added by 5.5. Okay, this will be subtracted by twice the value of the depth, which is 1.8586. 1.8586 plus width B, which is 3.7172 meters. So solving that, will have our savings in lining. Okay. So 2 times 1.3 okay, plus 5.5. 2 times 1.8586 times 3.7172. Okay, added plus. Okay, that's 0.6656. 0.6656. Okay, so that's the perimeter per unit length. But again, for lining, um, since we don't have a given total length of this rectangular channel, okay, so it means that savings per lining is a unit of length. So we will express this again in unit of area per unit length. So let's just multiply this by 1 meter, the total length. Okay, so it means that the savings per 1 meter, when we lay out the lining of smooth stone, we can save 0.6656 square meter of lining in every 1 meter. Okay, so in every 1 meter length, we save an area. Okay, the area of this lining. So we save an area of 0.6656 square meter. Okay, so next, again, let's review before we proceed. Uh, for the flow rate, just use the Manning's formula. That's the usual formula being used for open channel, especially in board exams. But unless indicated there to use the Chesi, we will use the equivalent formula for that. But usually we use Manning's formula for determining the Q. Then for letter B, the savings in earth excavation. So usually in excavation, um, the unit that is being determined for excavation is in a unit of volume. Okay, so uh, again, since we don't have a given total length of this channel here, so we cannot really determine the total volume that is being saved here using the economical section. So that's why when we compare the two, so we just simply subtract the area, then we have uh, a 1 meter width, okay, a unit length of 1 meter width. So if we want to really express this in a unit of volume, so we multiply 1 meter on this different in area, which we will have an equivalent of 0.2412 cubic meters. Okay, so it means that in every 1 meter we save a volume of 0.2412 uh, cubic meters of excavated soil. Okay, so because it matters in engineering, the cost, especially the cost for excavation, uh, being computed in terms of its volume. Okay, so that's why uh, usually in the problems in board exam, the unit is in square meter because it means that we have 0.2412 cubic meters in every 1 meter per 1 meter. That's why it is cancelled out. We have an answer of square meter. Okay, so for letter C, for lining, again, just like this in the savings and excavation, for lining, uh, it is referring to this lining, okay, the wetted perimeter where we will put the smooth stone. Okay, so when we def we when we determine the difference in the wetted perimeter, okay, and we multiply it by 1, so we can express it in square meter, but it is in every 1 meter length. So we save an area of 0.6656 square meter per 1 meter, or of course the meter will be cancelled out. We save a 0.6656 meter of lining in a 1 meter span. Okay, length. So let's proceed. Next problem, we have trapezoidal channel has a bottom width of 6 meters and side slopes of 2 horizontal, 1 vertical. When the depth of flow is 1.2, the flow is 20.4 cubic meters per second. Letter A, compute the specific energy. So what is the specific energy? It is H, or we can also express it as E, equals to V squared over 2G plus the depth. So we don't have yet the velocity, but since we have Q here and the depth 1.2, so this is 1.2 depth and the bottom width 6 meters, so we can determine the total dimension of this trapezoidal channel. So if we have 1 is to 2, if the depth is 1.2, this horizontal distance here is 2.4, this is 2.4 meters. So we can now find the total area of this trapezoid. So 6 plus the total top width is 4.8 plus 6, that's 10.8. 10.8 divided by 2 multiplied by the depth 1.2. So that's the area. Okay. 6 plus 10.8 over 2 times 1.2. That's 10.8. 10.08 square meter. So energy, specific energy is velocity. So let's determine velocity. That's Q over A. So 20.4 divided by area 10.08 square meter. So the velocity is in meter per second. Okay. 20.4 divided by 10.08. Okay, the answer is 2.023 0.00238 meter per second. Substitute here, raised to 2 over 2 times 9.81 meter per second squared plus the depth of 1.2 meters. So the specific energy is 2.0238 squared over 2g plus 1.2, 1.40875. Okay, that's the answer. Okay, that's in meters. Okay, that's the answer for letter A. For letter B, compute the slope of the channel. So how can we determine the slope of the channel? Using Manning's formula. Manning's formula, we have Q equals to A over N R raised to 2/3 S raised to 1/2. Q is 20.4, area 10.08 over N 0.014, that is given. R, the hydraulic radius, is still unknown. So we will solve first the hydraulic radius. Let's solve it right here. Okay, area over wetted perimeter. So the area 10.08, okay, this is 8 over wetted perimeter. So we don't have yet this slant height. Okay, this diagonal side of this trapezoid. So using Pythagorean theorem, we will have 2.4 squared plus 1.2 squared. This is your diagonal here. Okay, since it is symmetrical, we will have the same value. 2.4 squared plus 1.2 squared, that's 2.683. Okay, so 2.683 multiplied by 2, because we have two sides, and the base. Okay, bottom width 6 meters. So our hydraulic radius is 10.08 over 2.683 times 2 plus 6, 0.8868 or 887, let's say 0.887 meters. So substitute it here, 0.887 raised to 2/3 multiplied by S, which is unknown, required is 2 1/2. So let's directly solve S. 20.4 is equals to 10.08 over 0.014 multiplied by 0.887 raised to 2/3 times S, variable x, raised to 1/2. Okay, let's solve for x. So the slope is 0.0094. Okay, that's the answer for the slope. Next, for letter C, compute the average shearing stress at the boundary. Okay, so I haven't discussed this yet on the PowerPoint, but the solution for the average shearing stress at the boundary is equals to tau, the unit weight of the fluid, say that's water, multiplied by the hydraulic radius and the slope. So say the liquid there is water, 9.81 kilonewtons per cubic meters, times the hydraulic radius, 0.887. 0.887, okay, multiplied by S, 0.0094. So the shearing stress is 0.887 times 0.0094. Okay, the answer is, this is in kilonewtons. So that will be in kilopascal, 0.08179 kilopascal, or in Pascal, we just multiply this by 1000. Okay, 81.79793, okay, Pascal. Okay, so just correction, this is 0.0094 as you can see on the screen. 0.0094. Okay, so this 0.0094. Okay, we will just move one decimal place. This is 0.0. Okay, 0.00817, or okay, 8.1793 Pascal. Okay. Okay, so here are the answers for this problem. Next problem, my last problem. Water flows in a trapezoidal channel whose bottom width is 2.5 meters. So let's say this is your trapezoid. We have a width of 2.5. One side of the channel is vertical. Okay, let's say the left side is vertical, and the other side is inclined at 45 degrees. Okay, it's inclined at 45 degrees. The slope of the channel is 0.002 and roughness coefficient is 0.011. Determine the depth of flow of the most efficient section. So let's say this is your channel now. Okay, this is your top width. So this is a trapezoidal section. So what are the requirements in order for us to have the most efficient section, or in order for us to obtain the maximum flow rate based on the given dimensions? So we have a given dimension of 2.5 meters. So we cannot follow there the most efficient should be the half of a regular hexagon. So we cannot follow that, since it is required here that one side is vertical and the other side is inclining 45 degrees. So again, the most efficient section for trapezoidal section is sum of the top width is equals to, the sum of the sides should be equals to the total length of the top width. Okay, so it means that, let's say this is y sub 1, this is y sub 2, and let's say this is b, or let's say x. So y sub 1 plus y sub 2 equals to x. Okay, so now what other given that we should consider in order for us to obtain the most efficient section? Because y sub 1, y sub 2, and x, too many unknown here, 3 variables. Okay, so if this height here is y sub 1, okay, this is y sub 1 also, and if we have a 45-degree angle, okay, this is y sub 1 height, so it means this distance here, that's the same as y sub 1, because 45 degrees, it means that the two sides except the hypotenuse of this triangle formed here are the same. So if y sub 2 is just the hypotenuse of the sides of y sub 1. So applying Pythagorean theorem, we can have the sum of y sub 1 squared, right? Okay, or 2y sub 1 squared. So y sub 2 squared. So take the square root of both sides, or we can also use trigonometric function to take advantage of the given angle. We use sine of 45 degrees is y sub 1 over the hypotenuse y sub 2. Therefore, y sub 2 is equals to y sub 1 over sine 45 degrees. So we can use this. Okay. So what else? We can express y sub 2 in terms of y sub 1. How about x? Can we express this in terms of y sub 1? Yes. This total top with x here is just the equivalent of the sum of 5 meters and the horizontal distance y sub 1. Okay, the horizontal equivalent component of this hypotenuse y is y sub 2. So therefore, another equation that we can get here is that the x is 2.5 meters plus y sub 1. Okay, so it means that based on this equation, uh, we can only substitute all the values here so that we only have one variable left, which is y sub 1. So y sub 1 over sine 45 equals to x, which is 2.5 meters plus y sub 1. Okay, next. Okay, so y sub 1 plus y sub 1 over sine 45 equals to 2.5 plus y sub 1. So the unknown y sub 1 is 1.7677 or 768 meters. That's the depth of flow for the most efficient section. Next is for letter B. Using the depth we've obtained, what will be the hydraulic radius? Okay, so in determining the hydraulic radius in our lecture, I mentioned there that is equals to d over 2. Okay, but it's better to always use the general formula if we already have all the given dimensions. So it's better that we use general solution for the hydraulic radius, which is the cross-sectional area divided by the wetted perimeter. Okay, so let's determine now y sub 2. Y sub 2 is y sub 1 over sine 45. So 1.768 over sine 45. Okay, so y sub 2 is 1.768 over sine 45. The answer is 2.500. Okay, 2.5 meters. Okay, so it means that x is 2.5 plus 1.768. So x is 2.5 plus 1.768, 4.268 meters. This is the answer. So for x, sorry. Okay, so let's determine now the area. Okay, the area of trapezoid, that's 2.5 plus x, that's 4.268 divided by 2 multiplied by the depth y sub 1, which is 1.768. Okay, again area 2.5 plus x over 2 multiplied by y sub 1. Okay, so finding first the area, that's equals to 5.983 square meter. Then the wetted perimeter, okay, wetted perimeter is equals to y sub 1 plus y sub 2 plus the base of 2.5 meters. So y sub 1, 1.768 plus 2.5. Okay, 1 plus y sub 2 plus 2.5 meters, also y sub 2 and 2.5. The wetted perimeter is equals to 1.768 plus 2.5 plus 2.5. Okay, 6.768 meters. Now we can solve now the hydraulic radius, which is equals to area 5.983 square meter divided by 6.768. Okay, so 5.983 over 6.768. So the answer is 0.884 meters. Okay, so this is your hydraulic radius. So as I've discussed earlier, the radius for the most efficient section is d over 2. So let's check if it is really d over 2, the hydraulic radius is d over 2. So we can verify it by multiplying the hydraulic radius by 2 in order for us to determine the depth, which is your depth here is your y sub 1, right? Y sub 1. So it should be 1.6768. So let's say we multiply this by 2. So our answer is 1.768, which is correct. Okay, y sub 1 is 1.768. When you divide it by 2, that is equivalent to 0.884, or just the hydraulic radius for this economic section. So the answer now is 0.884 for letter B. For letter C, let's now determine the flow rate. So for letter C, so this is for letter B. Letter A, flow rate, Q is equals to area over N, using Manning's formula, R raised to 2/3 S raised to 1/2. Okay, so the area is 5.983 over N, and the given N is 0.011. 0.011 or 0.884 raised to 2/3 S. Slope given is 0.002. Okay, 0.002 raised to 1/2. So the Q is equals to 0.983 over 0.011 times 0.884 raised to 2/3 times 0.002 raised to 1/2. Okay, the answer is 22.405 cubic meters per seconds. Okay, so before we proceed to the last problem, let me just have an additional formula for critical depth. for rectangular channel. Okay, so the critical depth is cube root of q squared over g. Also, it is equals to 2/3 of the total specific energy on that channel, rectangular channel. Okay, 2/3 h. So that's your critical depth. Another, uh, in order for us also to obtain the critical velocity, critical velocity is just equals to the square root of g, or the acceleration due to gravity, multiplied by the critical depth computed. Okay, so now let's proceed to our next problem. Okay, CE board, November 2015. A rectangular channel 6 meters wide has a constant specific energy of 2.2 meters. So let's say this is h, 2.2 meters. Calculate the critical depth. Okay, critical depth is 2/3 of h, or you can use E for the energy, specific energy. 2/3 times 2.2 meters. Okay, so critical depth is 1.467. Then that's for letter A. For letter B, the critical velocity is the square root of g dc. Square root of 9.81 meter per second squared multiplied by critical depth 1.467. So our critical velocity then is equals to the square root of 9.81 times 1.467. That's 3.794 meter per second. For letter C, what will be the critical slope having an n of 0.012? So we have already the critical velocity using Manning's formula. 1 over n, r raised to 2/3 s raised to 1/2. So that's our formula for Manning's. So based on our calculated values for the cross section of this rectangular channel, we have a width of 6 meters and we have a critical depth which is 1.467. Okay, so from that we can already determine the hydraulic radius, which is area over wetted perimeter. 1.467 over 2 times 1.467 plus 6. So the hydraulic radius is 6 times 1.467 over 2 times 1.467 plus 6. 0.985 meters. Okay, we can now substitute that in this formula. 3.794, the critical velocity, 1 over n, 0.012 or 0.985 raised to 2/3 and s. Okay, s is unknown raised to 1/2. So let's compute that. S therefore is equals to 1 over 0.012, 0.985 raised to 2/3, then s, let's say x raised to 1/2. Okay, the answer for the slope is 0.0021. That's the final answer for the critical slope. Okay, That ends our lecture. Thank you for watching. God bless.